Hello, today we'll be taking a look at maximizing the quality of white light with green correction. In this presentation, we'll be talking about using green correction to create high quality light with adjustable color temperature. To more fully understand one application of where this kind of correction is desirable, we'll be talking about circadian rhythm. But this type of hue correction can be used in any application of color temperature adjustable lighting. We will discuss the blackbody radiation curve and why it is important for color temperature adjustable lighting in applications like mimicking sunlight, paying special attention to correlated color temperature and the hue error that can occur when using LEDs. Finally, we will take a look at a few different methods correcting hue errors. This presentation will focus on adding green LEDs to the circuits that are generally used to do lighting with adjustable color temperature. We start with circadian rhythm, and this is just one of many applications where color temperature tunable light is desired. The circadian rhythm is the body's natural clock. It provides some of the timing for alertness, attention, sleeping, eating, and other body processes. The rhythm is affected by and synchronized to light exposure. The original timing was provided by daylight, and there is a lot of interest in the effects of artificial lighting. To have artificial lighting more closely resemble daylight, you need to control several properties of the light. These include the intensity, the timing, the duration, and the wavelength of the light. With modern controls, the intensity, timing, and duration can be easily controlled. The last part, the wavelengths of the light used, is what we will focus on for this presentation. All of these categories are interrelated, so while we discuss the various wavelengths and color temperatures of light, it's also important to realize that we will also need to control how much of each color we use, when we start using a particular color, and how long we use that color for. The sun was the original clockmaster of the circadian rhythm. The timing of the sunrise and the sunset, along with sunlight exposure in the middle of the day, all work to control the timing of maximum alertness and attention, as well as the timing of tiredness and sleep. When humans discovered fire, we began to have a little more control over some of these things. We've come a long way from using fire for artificial lighting. We're gonna skip over all of the intermediate forms of lighting, as almost all of our lighting is now electric in one form or another. And today we'll be focusing specifically on LED technology. There's a lot of interest in the effects of artificial light on the circadian rhythm, and also on more closely recreating daylight to minimize the negative effects of artificial lighting. With LEDs, it becomes possible to tune the color temperature from an orangish light all the way to a bluish light. We can recreate the oranges of sunrise and sunset, the yellows of the morning and afternoon sun, and the bright white of the sun at noon. Next, we'll take a look at the physiology of the eye. In the back of your eye, there are some specific cells used for vision. These are the rods and cones. The rods generally are sensitive to brightness and help you define shapes. The cones give you color vision. These, along with your brain, make sense of the light that comes into your eye and the images that you see. We're gonna follow the path from the eye to some of the circadian elements of the brain that we are interested in. And we're actually not going to start with the rods and the cones, that is the normal vision, and instead we're going to start with the intrinsically photosensitive retinal ganglion cells, which is commonly abbreviated to IPRGC. These retinal ganglion cells are the cells that collect the information from the rods and cones in order to send that along to the brain. However, some of these cells, it's a small percentage, are themselves sensitive to light. These signals aren't necessarily used in vision, but rather are sent to a specific part of the brain that handles the circadian rhythm. These intrinsically photosensitive retinal ganglion cells are slower to react to light. They're not generally used directly in vision, and they're most sensitive to blue light. That's going to become important just a little bit later in this presentation, but that's the general portion of the spectrum that these are most sensitive to. Those signals go along the retinohypothalamic tract. This delivers the circadian information to the suprachiasmatic nucleus, and this is the portion of the brain that is the circadian pacemaker. So this is taking information from these iPRGC cells in your eye. These iPRGC cells are just kind of keeping track of how much light has entered the eye. And in turn, this SCN, that's the acronym for the suprachiasmatic nucleus, is going to send signals to other portions of the brain, and the one we want to focus in is going to be the pineal gland. This produces melatonin, which helps you sleep, and in particular during the day, the SCN sends a signal to the pineal gland to suppress melatonin. That helps keep you alert and awake during the day. In terms of circadian effects, we're most interested in things like attention, which is alertness and focus. And so if you are following the standard circadian rhythm, the melatonin secretion is going to be stopping somewhere around 7:30. So that's when you should be starting to become quite alert and awake. And high alertness begins around 10 in the morning. So this here is attention. By a little while after noon, we also have things like your best coordination and fastest reaction time. And as we get into nighttime, when your eye stops seeing light, that undoes the suppression of melatonin, and you begin to get into the sleep portion of your circadian rhythm. The circadian rhythm is going to control not only the timing of your sleep, but also the quality of your sleep. And because this whole system is most sensitive to blue light, this is one of the reasons why they tell folks not to be in front of screens just before bedtime. If you're in front of a screen, a lot of the screens have a good portion of blue in the backlight. This can cause additional melatonin suppression so that when you do finally go to bed, you don't actually get a good level of melatonin, and so your timing and your quality of sleep can suffer because of that. All right, now we want to take a look at applications that involve various adjustable correlated color temperature. The abbreviation for that is CCT. CCT is given as a temperature in Kelvin. That's essentially the Celsius scale, but it starts at absolute zero. And the numbers are fairly large and typically see things in the thousands of degrees. Now, this here is a diagram showing a color chart, and on the color chart is a black body radiation curve. This is sometimes also called the Planckian locus. And what this does is this tells you if you heat up an object to a certain temperature, what color will it glow? So if you think about taking a chunk of iron, for example, and you start heating it up, well, eventually it starts glowing red. And so we see that on our chart at around 1800 Kelvin. We're kind of going from red to orange by that time. And as we keep heating it up, we go from orange into yellow, and then from yellow into white, and then from white into bluish white. For those who are in astronomy, they'll actually be somewhat familiar with this scale because this scale is also used to tell the temperatures of stars. If you have a bluish star, that's going to be a much hotter star than a yellow or orange star. The portion of this diagram that we're generally going to be interested is the range from around 2700 Kelvin up to around 6500 Kelvin. This is the range that ANSI has standardized. We'll take a look at the ANSI binning in just a moment. But one of the important parts I want you to get from this graph here is that the correlated color temperature, the reason why they call it correlated color temperature is because there are some light sources, LEDs especially, that may not fall exactly on this black body radiation curve. Some of our older technologies, like light bulbs, for example, always fall on this black body radiation curve. And that's because they actually work by heating up a small piece of metal. They heat up their filament until it is so hot that it really does glow that color. And for our standard 60 watt incandescent bulb, we're just under 3000 Kelvin. So that's kind of a yellowy white. The CCT, the correlated color temperature, doesn't fully capture the hue information. And there can be what's called a hue error if you are above or below the black body radiation curve. One important part about that is some folks confuse CRI and being exactly on the black body radiation curve. However, it is possible to have a pretty high CRI and also have hue error at the same time. So the CRI is not a super good measure of how well you're following this black body radiation curve. I also should note on this particular chart that is here, if you look in the lower third or so, there should be a spot that you will identify as white. However, it's most likely in the wrong location. And that is because most display technologies cannot properly display this chart. That white section should actually be somewhere between the 4,000 and 6,000 marks on that curve in the center there. For my display, for example, it's a little bit low and a little bit to the left. If you put it on a projector, for example, which uses a different technology to make the light, if you have like a DLP projector, for example, it'll be in a different spot. And if you try to print it out on paper, which uses yet another process, that's CMYK or cyan, magenta, yellow, and black in order to create the image, that white spot will again be in a different spot. So because it's going to be slightly different for everybody, what I really want you to take away from this is if we look at the black body radiation scale, which is at the top of the slide, you can see that the colors that we are interested in to recreate sunlight, for example, is going to be from orange through yellow, through white, and through blue. And those are the only colors that we're generally going to see when we're talking about black body radiation. The colors that you don't see in that scale, but are fairly prevalent in the color chart itself, are going to be green and purple or pink color. And you'll find those if you go above the black body radiation curve and if you go below the black body radiation curve. Anytime we have lights that are not exactly on this curve, they typically will have a slight hue to them, and it's generally going to be slightly green if we are high above the curve, or slightly pink or purple if we are below the curve. There are going to be times where this may not matter very much, but there are going to be other times, which we'll discuss in a moment here, where this is going to be a lot more of an important factor. Now, we're going to zoom into this chart. We're going to zoom into the 2700 Kelvin to 6000 Kelvin. You can see that's kind of in the middle of the black body radiation curve, and we're going to zoom in there. So the next few slides are going to be well zoomed into that area. Just note that the 2700 Kelvin is orangey white, and the 6500 Kelvin is a bluish white, and that'll be the range of this chart that we're going to be looking at. In order to standardize when folks are buying LED technology, ANSI has come up with a set of ANSI bins for these various color temperatures. You can see in the legend down on the lower right of this chart, we have boxes for 2700 Kelvin, and then from there they start at 3000 and go up by 500s, right up until near the end where you hit 5700 and finally 6500. We also have that Planckian locus or black body radiation curve, and you can see that kind of slices mostly through the center of these bins. However, when we get to the cool white section over on the left-hand side, that's the 6500 Kelvin section, the Planckian locus is closer to the bottom of that chart. While this is not a particularly colorful chart at this time, I just want to let you know if you are above these bins, then you're going to be in the green hue area, so that's been labeled on this chart. If you are below these bins, you're going to be in the pink and purple hue. So the LEDs can be a little above or a little below, but they're not supposed to be by too much. And the whole purpose of these ANSI bins is to make it so that if you buy a 3000 Kelvin lamp from one manufacturer, you can also go and buy a 3000 Kelvin lamp from another manufacturer and have them be approximately the same color. It may not be exactly the same color, but unless you have them right next to each other side by side, it should not be a difference that is so discernible as to be distracting. So when we talk about tunable white, we're interested in controlling how much blue and how much orange color we have with our white. And so we're going to be interested in being able to adjust between these ranges. Some folks use a small range, so they might use only maybe 3000 to 5000 or maybe 3500 to 5000. Other folks want the whole wide range. And that's what we're going to talk about today, is when you want the ability to go anywhere between 2700 Kelvin, that's going to be a dimmed down 60 watt incandescent bulb. In fact, maybe a 40 watt incandescent bulb would be a closer fit to that. It's going to be kind of an orangey white, all the way to a bluish, sterile looking white. And that's going to be the 6500 Kelvin. Now, when you purchase LEDs, the LEDs are going to be at some spot. They should be within these ANSI bins. Pretty much all the LED manufacturers nowadays have figured out how to get their bins to match the ANSI bins. So when you go to order a particular color of white, you can choose one of these bins, and many of the LED manufacturers will even allow you to order sub bins. So you can actually make sure that you're in a particular zone of these. But you might be above or below the black body radiation curve. And so in this case here, I have one little blue dot here, one little blue triangle showing an LED that we might have gotten from an LED manufacturer at 6500K, and that one's right on the Planckian locus. So that's over on the left. And then over on the right, we might have also purchased some 2700 Kelvin LEDs, and this one I'm going to show just a little bit below the Planckian locus. And in fact, most of the LED manufacturers put their bins so they straddle the Planckian locus, so a lot of times you'll be getting an LED that is slightly above or slightly below. So in order to make a color temperature that is between these two, we simply mix the warm and the cool white. If we wanted something in the 4000 Kelvin range, which is in the middle of this chart, we can just mix half warm and half cool. And this allows us to make any color in between those two. However, it only allows us to travel in a straight line. When we do this, if we're using LEDs that are near the extreme ends of this range, we tend to leave the ANSI bins. We tend to be below the ANSI bins. And if you remember from our color chart we were looking at previously, if you go below the Planckian locus, then you end up in kind of that pink or purple tint area. And this is going to be the worst in the middle of the range. So it is around that 4000 Kelvin that you are going to be the furthest away from that point. And so we're going to call this distance from the Planckian locus to a particular color that you're making at that moment the hue error. So that's going to be how far away from the Planckian locus. We're going to be calling that our perfect light that we want. And how far away you get from that is going to be the hue error. We'd like to do something about this hue error. And there are several different methods that we can use to manage this. So this is what you would get if we just have warm white LEDs and cool white LEDs together in a luminaire, and we're mixing to create the color temperatures in between. There are some fairly complex methods that can be used to manage the hue error. Many of these will use a bunch of different LEDs. So some examples are going to be something like a red, green, blue, and amber LEDs, or possibly red, green, blue, and white. The photo on the left, for example, is a multi-chip LED, and it has inside of it a red, a green, a blue, and a white LED die. And those are individually controllable, so you can individually mix them. If you're trying to do something like color temperatures, you'll typically use the white that is in there. I think this one is around 4,000 Kelvin, so it kind of starts in the middle of that color diagram. And you then use the other colors in smaller amounts to kind of move that point around on the color chart. If you want to get more into the bluish white, for example, you would use that white LED plus just a little bit of blue to move that color point over into the blue section. If you want a more yellow light, for example, you might start with the white LED and you would add some red and green. For those of you who worked in theater and managed lighting, you'll know that if you mix red and green light, you get yellow. And so that can add yellow hue to your color and let you again move it around through the color chart and through the color space to stay near the Planckian locus. You also could use multiple CCT, that's multiple color temperature, LEDs. So you might have some cool white, like 6,500 Kelvin, something in the middle, maybe 4,000 would be a pretty good choice, and then something in the warm section, like 2,700. And you would simply mix from 2,700 to 4,000. That lets you go in a straight line, but you'll stay in the ANSI bins. And then from the 4,000, you would then start mixing with the 6,000 Kelvin to move down into the cooler whites. One of the issues with all of these is that this ends up being quite costly, and it's because you end up having LEDs that you're not using, that are not lit most of the time. And so if you're trying to make cool white, for example, you're probably not going to be using any of the red. Or if you're using the multiple CCT LEDs when you're over in the cool white section, you might not have the warm white LEDs on at all. However, those cost money to put on the board. So what I'd like to propose today is using just green in addition to your warm and your cool LEDs in order to fix this hue error. And how advanced you might want to go with this depends on how much correction you might need. So let's talk about the simple green correction first. This is kind of the simplest method, and this is to add a fixed amount of green. What this essentially does is this takes that straight line that you were in, and if you remember on our color chart from before, green is up near the top and a little bit to the left on that color chart. That's going to move us up and a little bit to the left on this chart as well. This gives us much better hue in the middle of this curve, so our hue error there is quite small, and we're nicely near the center of these ANSI bins. The closer you can stay to the center of these bins, usually the better. And in reality, we're really trying to follow that Planckian locus curve, that black body radiation curve. One thing you'll note, though, is that this actually makes our hue worse at the ends of the line, particularly over in the cool white section. That extra green might be undesirable. And when we talk about these hue errors, we also need to take into account what else is going to be visible in the room when these lights are being used. And that's because the eye does something called white balancing. When you're in a particular room, your eyes and your brain will look around and see what the average of the light is. And over time, your brain picks an average and calls that white. If you change rooms, or maybe you go outside or come inside and you go into an area where there's a different hue to the light, then it's very noticeable when you first walk in. However, once you've been in there for a while, that your brain averages that out. In some circumstances, if all the lamps are the same color, or if they change slowly, this may not be as big of a deal to have some of this hue error. Where it really comes into play is when you have to play nicely with other fixtures, in particular when you have to play with other luminaires that are not adjustable color temperature. If there are some 4000 Kelvin lamps in the room, and they're going to be visible while your lamps are also lit, then you want your hue error to be as small as possible in that zone. If it isn't, then the person who's in the room will see the 4000K lights, and they'll see your lights, and your lights will be noticeably pinker or purpler than the other ones if you leave that hue error uncorrected. In the same vein, now if you're over on the 6000 Kelvin or the 2700 Kelvin ends, we're going to be above the black body radiation curve, so your lamp will have a green hue when compared to something that is on the black body radiation curve. The best method here is to use what's called proportional green correction. We're going to be using warm, cool, and green LEDs. However, the amount of green that we use is going to be proportional to the hue error. So when the hue error is large, we're going to add more green. And when the hue error is small, we will use less green. This generally ends up with less green on the ends. So over in the cool white, that's the 6500 Kelvin section on the left, we're using nothing. If we're at that 6500 mark, we're actually a little bit past that for that dot. Over in the 2700 section on the right, we have some, and in the 4000 section, 4000K section in the middle, we have the most correction. So this is going to be kind of more in the middle, less green on the ends. And using this, we can follow the black body curve. We can actually follow this fairly precisely just by controlling where we are on the black body radiation curve. So if you have some kind of control that allows you to control the color temperature, your green will be designed such that there is more green in the center and less green on the ends, in addition to the warm and the cool LEDs that are there. This proportional green gives a much better quality light in terms of following the black body radiation curve. And you can get the hue error minimized to a very small amount. We're talking like 0.002 du prime v prime for the hue error using this kind of method. Now, when you're doing this, some people may wonder what the effects on something like CRI are going to be. And so the color rendering index is gonna mainly depend on the CRI of the warm and cool LEDs that you use. The green correction does make it better, but it's really an insignificant amount. It's just a minor boost of 2 or 3 percentage points. And so it's going to depend on which LEDs you start with. So you want to make sure that you start with high CRI warm white and high CRI cool white. Also, the green that you choose, the particular wavelength of the green that you choose, will set the direction that the correction occurs in. You'll also ultimately want to have LEDs that are close to or below the black body radiation curve. So when you're taking a look at your order codes for ordering LEDs, you want to make sure that the bins that you are selecting are close to or below the black body radiation curve. If you started near the top of the ANSI bins, adding green can only push you up and to the left on the color chart. So you'll essentially have 0 green added and you'll still be having a slight green hue to your light. So the LEDs that you start with are really, really important. However, the greens don't have to be high power. The greens can be a fraction of the power. If you were using 1 watt warm and cool LEDs, for example, you could easily use half-watt green LEDs. If you're already using half watts for your warms and cools, you might be in the 1/10 of a watt class for your greens. So you really only need a small amount of green in order to do this hue correction. So to review, for adjustable color temperature is something that's definitely desired for circadian rhythm. That's not the only place that it is desired. We also see things like adjustable correlated color temperature for things like dim to warm. or applications where someone just wants adjustable color temperature. And the standard method that just mixes warm and cool to make all the color temperatures in the middle tends to have a large hue error at 4000 Kelvin. That's the middle of the range. The addition of green can greatly reduce this hue error, and it's not complex to do. If you already have the complexity of having adjustable correlated color temperature, then it's usually not much more additional complexity in order to add this green correction. Thank you.